I've still got 1 minute. I haven't started yet. Just showing some eye candy. Okay, looks like we have reached 12:45, and I'll go ahead and get started. So I just want to talk tonight about agent-based modeling and simulation. Um, I've been meaning to do this presentation for quite a while, but it's quite a heady topic and also a very full topic, meaning there's a lot of directions that you can take um, take your interest in this kind of area, and then also a lot of approaches, a lot of techniques, lots of different mathematical premises upon which you can uh, base your work in agent-based simulation or modeling. But primarily for architects, it's kind of a simple thing. It's essentially trying to understand how people are going to use your space and being able to do so with the simulation software prior to construction. Um, and there's kind of two approaches to this. There's the approach that's based on kind of the pre-built model, something where the architect has designed and built the model, and then we're able to take that existing model and then kind of put agents into that model. And then the other kind of method is to have a piece of software that's built from the ground up for agent-based modeling, which you would need to kind of reconstruct whatever has been constructed by the design team in this other piece of software. And I think that the kind of split, it happens between those who are professionally interested in agent-based modeling as a kind of a psychological or from a perspective of a consultant, a paid consultant that's really focused on agent-based modeling, versus a design team who's kind of interested in seeing where the bottlenecks in a space are. And so you can see here within this comparison chart, thanks to Wikipedia, that there are many different agent-based modeling softwares out there that one can use to kind of test your space, right? But most of these are the first method that I talked about, where if you were a design team, you'd have your design model, but then you would have to rebuild that model in these pieces of software, which for the most part, which is kind of a barrier to entry, I'd say, meaning that the rebuild time between the softwares is somewhat prohibitive for a fast-paced design team who's looking to iterate quickly. So with that said, I've tested 3 agent-based modeling tools, and 2 of them are based on the model of the designer, and the third is based on software found from other research and taking into consideration the different benefits and drawbacks of some of these ones. And so I kind of zoomed in on this AnyLogic, and there's a lot of things that I liked about it, but just to kind of go through that quickly to give you a sense of what the software is like. Here's the software, and essentially This is one of their tutorials that or one of the pre-built features that they've provided. And there's a lot of different aspects to the software, but essentially this here is where someone would create kind of a dashboard within which someone could kind of analyze the space. So here we're looking at a subway platform, and so once you kind of push play in the software, it brings up that dashboard that has been created. And before we hit play on that, there's kind of a lot of different pieces to this. And here, once I do hit play, it kind of shows you a little bit about that. So here we go. And forgive me, things might run a little slow. So we have the pedestrian logic, and which is here, and then the train logic, which is here, and then the animation. And the animation is time-based, and essentially it shows you where your bottlenecks will be hypothetically based on inputs and outputs that you provide the system. But they have kind of these pre-built logics that are given in the piece of software, such as this pedestrian logic and the train logic, which allow you to kind of quickly put together a simulation that could be somewhat useful in terms of flows of people and bottlenecks. Like I said, the drawback to this method is that you're going to have to take your designed iteration and redraw it in their system with their proprietary drawing tools that are not necessarily as intuitive or as powerful as some of the design tools we're used to using. And I think that can be a real drawback to this type of method, even with their increase of capabilities in terms of pedestrian logics or car logics that they have kind of built into their system. So you can see over time it shows you kind of the buildup of the different traffic and where these kind of main flows of people would move in the space. So I think you get an idea for yeah, go ahead, Rob.
A little slow behind your audio.
Okay, yeah.
Blast out the entire office and describe agency simulation
You'd like me to describe agent simulation?
as being like sort of traffic flow of people or cars, but the reality is it could be collision of raindrops, right? You know, can you sort of generalize that in a way that people understand the general subject?
Sure. Yeah. So I'm sorry if my audio is kind of laggy. I've got Unreal Engine, Rhino, and then this piece of software open all at the same time. It's using a lot of resources on top of the recording and the video projection, the video feed that I've got. So sorry about that. But thanks, Rob, for the question. By way of kind of introduction, agent simulation is let's see, kind of a theoretical field, mathematical theoretical field of trying to simulate a body in motion, and that body can be anything. Like Rob mentioned, it could be a raindrop, it could be cars, it could be people moving, it could be plasma in a nuclear reactor. It takes into account fluid dynamics properties and those types of things. And then also, in addition to that, depending on the sophistication of the simulation software, you can start to kind of parameterize the characteristics of the agents. And you can set parameters for the amount of randomization within the paths that the agents will take, or the standardized paths that the agents will take. And that's kind of what's built into to these logics, like the pedestrian logic, is a certain amount of randomization in paths of travel, speed of the agents. So you can set a domain for the speed of the agent. Those types of things are kind of built into the logic upon which an agent simulation would be built. Now, also to just kind of reframe and to go back a little bit in terms of why this would be useful to architects, we're always looking for feedback on the use of our spaces, and it's really kind of difficult to get that, especially in the litigious society in the United States in which we operate a lot of the time, or some of the time anyway. People aren't interested in kind of handing over information about the performance of spaces so readily, because there's a chance to get sued over that. But anyway, so agent-based simulation gives us a small window into the performance of the space in terms of how a human would use it, or how crowds of humans would use it. And so we can use agent-based simulation to kind of simulate those uses of spaces over time. Does that answer your question, Rob? Would you like me to specify in what I talk about anymore in that?
No, that was
Okay, great. So one of the drawbacks of agent-based simulation is similar to film. When you're editing film, you're confined by the media, and the media is time-based. And because it's time-based, it requires you to kind of tease out the time it takes for those agents to move through space. Now, obviously, you can speed up the amount of time that's, the time step, but even still, because it's a time-based simulation, it requires you to kind of move through the time that that you're interested in simulating, and because of that, kind of makes it so it's a substantial time commitment to do any sort of agent-based simulation modeling. Okay, so now we'll move on to Unreal Engine, and there are many. Oh, let's see. It looks like my audio is lost. Check, check, test, 1, 2. Okay, looks like my audio is restored. Looks like my audio is restored. Okay, so there are many video gaming engines, and because people are interested in gameplay where you have an enemy, it's kind of an obvious use case for an agent-based simulation where you're trying to create the enemy that is somewhat intelligent in its movement and in the way that it that these agents would move through a space. So something like Unreal Engine. Let's see, audio is lost again. I'm going to close any logic. I'm done in that program. Hopefully that will help. Okay, it looks like my audio is restored. Okay, so there are many video gaming engines. Unreal Engine happens to be one of the video gaming engines with the highest quality uh, graphics, and because of that, it's kind of an obvious choice for a high-end architectural firm. Although I would say that Unity is a little bit easier, a little bit lower barrier to entry, and I haven't in quite a long time tested Unity's AI or its agent-based simulation models, or the ease of which one can implement those systems. But I have spent some time here with Unreal Engine, and it's quite a complex system, and it takes a lot of effort to try and get the system set up. But once you have the system set up, it's fairly real in terms of the visualization, and there's a lot of flexibility with which you can develop the agent-based simulation. So I've kind of set up this kind of false world, or this kind of place for testing, and I'll show you kind of different aspects of the test. The first thing that you'll notice is this green space, and the green space is looks like my audio is lost again. Is that true? Can you hear me? Hello? Looks like I'm back. Okay. So the green space is essentially computed every time you manipulate the environment. And for us architects, it's really nice because Unreal Engine allows us to import our models directly into Unreal Engine. So we can kind of start with a model that we've developed, which allows us to iterate more quickly with an agent-based simulation tool as kind of a design guide. So the looks like my audio is lost again. So the green is an automatically computed kind of uh, groundwork upon which an agent can move. And so if I change one aspect of this space, it will recompute the um, that the space with which we can operate. So you see the red, that shows us where people can move. So if I move this wall here, um, it's going to create red uh, outside of the area where we can move. Now, it's showing that people can move way back there beyond this wall, but people can't get back there. And I guess what I have to do is I have to make this floor smaller, and then that will change where people can move, where these agents can move. So um, now let's see. I'm just going to run the simulation so you can kind of see what happens, and then we can talk about what I've done here as it runs. So basically, I've programmed several different agents to do different things. Some of them move faster than others. Some of them are programmed to go to different locations than others. And then some haven't been programmed yet that are just standing here on the right. Essentially, what I have here is the green space. I have some different obstacles that the agents move around, and then I have this red bar, and this red bar is kind of like a no walk zone, where they kind of have to go around the red bar in order to get to the location. And so if I kind of click on one of these guys over here and zoom in, you can see the agents are pretty lifelike, and you can put a skin on these people, so they're even more. They kind of have, video game enemy look to them, and you can make them look kind of harmless. But anyway, So here we see that same simulation happen again. Oops. Now, if I stop the animation and I move this barrier here, this artificial barrier, let's say I rotate it, it will then recompute the path or the available space for which people can move, and it will affect what people do. Now, not all of the agents are programmed to actually obey this red marker. Some of them will just ignore it and go right through it. But some of them will actually listen, obey this red marker. So here we go. If I press play, you'll be able to see these agents try to move around that marker. One of the issues that I haven't been able to solve yet, and again, I haven't spent a lot of time on this recently, but when I was anxiously engaged in this particular pursuit, I had a hard time finding a way to get agents to kind of go away as if they left, pretending as though an agent were to leave the building. For example, I I wasn't able to get that logic taken care of. Just so you have an understanding of what's going on in the background, I'll show you kind of some of the different parts of this. There's each agent uh, has kind of has the facade of the agent, this the character, but then behind the character is a logic. And here's this event graph for this character, and it's got kind of a similar kind of interface to Grasshopper, but it's a little bit more, what's the word? Uh, it's a little bit more of a tree than Grasshopper is, in that one graph isn't necessarily the entirety of the. Hello, hello. Looks like I'm back maybe. So as I was saying, there's a lot of opportunity to iterate quickly because you can make adjustments in the model rather fast. Like I was just showing you, where adjusting kind of barriers can be done quickly, and then agents will respond to those changes without having to adjust um, the internal logic of the system too drastically. Now, another thing that we can do is you can choose these waypoints. Here's a waypoint here, and if I make an adjustment to the waypoint, then it will make an adjustment to the path or the goal of the agents. So just adjusted that waypoint, and if I hit play, then it adjusts the path of the specific agents that are interested in that place, or interested in that set of rules, right? So here we have kind of a set path that these agents are going to follow. And these agents that we're looking at here, they are all they're all programmed to go the same speed, and because of that, they're kind of in this line. But if you adjusted the speed of the individual agents, then it would feel more varied and more like there was freedom in terms of the movement of the individual agents. So there are some really big benefits to using a video gaming engine in terms of visualization, but there are some drawbacks in that you don't have the same level of kind of feedback or information that you can pull out of the model in the way that maybe a software tool like AnyLogic provides. And that's kind of where I feel like Grasshopper shines, because it provides some of that data analysis feedback that we want, that something like AnyLogic does, but it doesn't require us to rebuild the model like an AnyLogic piece of software wants us to. So if your purpose is for a nice visualization, then Unreal Engine might be the tool for you because of the quality of the agents. You know, the agents feel pretty real, and there's kind of this real-time feedback with the system that isn't quite available with something like an AnyLogic. So moving on to the tools within Grasshopper, there's two or three really good tools within Grasshopper. The one that I've used is called Quelia, and it's been around since 2015 or 16. The latest version is 2016, so it hasn't been updated in a long time, but there's still a lot of merit to its system. And so I'm going to talk about a little bit about Quelia and how it works and what it can do. Like I said, one of the nice things about it is that it allows you to get a little bit more information out. For example, I can set parameters such as how many agents will be created per time step. And so in this one, it's 26 agents will be made every time step, and the time steps are set at 20 milliseconds. So, you know, you can do the math real quick and find out how many people are going to be entering the space at interval or over time, which can be really useful for a shopping mall or a hospital or transit station. These kinds of numbers can be really powerful for a client. So essentially, what I've done here is I've taken one of our projects, the lobby of one of our projects, and I've kind of stripped it down and made it a little more simple for us to kind of use as this model, remove the facade, and then kind of simplify it in terms of where people can move, just for ease of use here for the simulation. And then, as you can see, there's kind of two different branches. There's this top one here, and then there's this bottom one here. And they're the same logic duplicated. And so what that gives us is agents coming from the elevator core and people coming from the front doors, essentially. And you can see here, this red line is a line-based emitter, meaning it's emitting agents from this line into this area. And similar to the Unreal Engine environment, when you create, you have to kind of create the space in which the agents can operate. So here, this is the surfaces that the agents can operate inside of, essentially. And there's kind of some gymnastics you have to do in order to make sure this works. For example, I actually have a different surface than the whole surface. I'm not using the entire surface as the area where the agents can move. I've removed this section behind the desk because agents were getting stuck back here. So you kind of have to think for the agents a little bit. They're in some ways kind of dumb. So there you can see kind of the area that people can move, and essentially, you know, you've got these two logics, one coming from the elevator core, one coming from the doors, and then here's kind of the engine, which is the Quelia system, and it's a little bit different in terms of the build logic than some Grasshopper scripts. Some Grasshopper scripts, it's kind of a left to right proposition, but Aqualia logic is based somewhat around the middle, around this node, this system node. So what you end up with is a lot of things that are kind of perpetuated beyond this main node that kind of feed back into the node, this system node, in a reverse fashion. So you can set parameters over here, and it affects everything that happens prior to it. So that's just kind of some build logic that's important when you're setting up a Quelia system, is that it's a little bit counterintuitive in terms of the way that you build the logic within Grasshopper, meaning that it flows back. Some things flow backwards. Some of these options and parameters flow backwards. So, right, what I've got here is I've got this one Boolean that turns the system on. And so if I toggle that Boolean, you'll start to see the agents start to fill the space. And like I said, it's a time-based it's a time-based proposition, and because of that, we have to kind of wait for it, and it gives you the unfolding of how this might happen over time, and the agents kind of roam randomly. Yeah, so Will's pointing out that some of them go through the columns. So what happens is you kind of create an inertia, or an amount of energy that the agents have moving forward, and when they see an obstacle, if they're moving too quickly, they won't be able to stop in time, essentially. And that's a fine tuning of the parameters, Will. So this is not a perfect model by any means, but it gives you an idea of the way people might somewhat move through the space. There are other ways to kind of solve that problem. For example, like I was showing you, that surface, you could Boolean out the locations of those columns, which would allow the agents to not be able to go through the columns, because they wouldn't be able to move through that space. So that's one way to try and do it. But essentially, you really have to orchestrate the space in a way that you're going to get the information you want. Because if you don't orchestrate it exactly how you want it to be, you'll end up with a lot of unexpected results, like people walking through columns. Another example, Will, since you're asking questions and listening here, in order to get the agents to go up the right escalator and to go down the left escalator, what you have to do is you have to disable the left escalator for the agents that are coming up, and you have to disable the down escalator, or sorry, the up escalator for those agents that are coming down. So these agents don't even have the option to go up this left escalator if they're coming up the escalator, and vice versa for these other agents. One thing that is a little bit easier to do within Grasshopper with these agents is to kind of set a deconstruction of the agents after a certain amount of time, or if they reach a certain destination, which, like I was saying, was a little bit more difficult within Unreal Engine. And so with this kind of simulation, I think you can get quite a bit more information out of the simulation than you can with the Unreal Engine. But the Unreal Engine is really dynamic in terms of the real-time capabilities of adjusting geometry, and then visualizing how the agents react to that geometry. Within Quelia and Grasshopper, that turnaround time isn't quite as quick. You have to do more back-end kind of manipulation before you can achieve the same amount of feedback. Now, when I first started the video, I was showing you this particle simulation within FlexHopper. It's new. When I was doing this research last year, it was still in beta. Now it's out of beta, and I'd be really curious to have someone try out FlexHopper. I haven't had the chance to do it. I'd like to do it in the future, but I haven't really tested it. It seems like FlexHopper has way less computational restrictions in terms of it's not as computationally as expensive as Quelia. At least that's what I'm kind of gathering from these animations. My question about FlexHopper is its ability to operate in 2 dimensions, similar to a grounded person simulation agent. So that's kind of the big question that I have about FlexHopper. Can it operate in a similar way to a human agent? So anyway, this is kind of just going over some of the different options in terms of agent simulations. I'd love to take any questions real quick before I end this call. I'm really sorry for the technical difficulties. I know I've lost several people. I'll try um, to edit this video before I post it on YouTube so that we only get the real content and not all the technical difficulties. But anyway, let me take any questions you might have before I get off the call. I'll make these files available within the links so that you can download and try each of these simulations yourself. Let's see. Will's asking me something about Wes with the Unreal portion captured. Did we capture the Unreal portion? Yes, the Unreal portion was captured. So that was captured so that we can you can view it in the YouTube. So that yeah, we'll have that available for you. Sure. Well, anyway, thanks so much for your time today. Again, I'm sorry for the technical difficulties. Internet cut out, but thanks a lot. Have a great day.